my dear students, welcome to Teacher at Home. Today class we are going to learn the fourth chapter, Structure of the Atom. In chapter 3 we have learned that atoms and molecules are the fundamental building blocks of matter. The existence of different kinds of matter is due to different atoms constituting them. Now the question arises, what makes the atom of an element different from the atom of other element? And 2. Are atoms really indivisible as proposed by Dalton, or are there smaller constituents inside the atom? We shall find out the answers to these questions in this chapter. We learn about subatomic particles and the various models that have been proposed to explain how these particles are arranged within the atom. A major challenge before the scientists at the end of the 19th century was to reveal the structure of the atom as well as to explain its important properties. The elucidations of the structure of atom is based on the series of experiments. On the first indication that atoms are not indivisible comes from studying static electricity and the condition under which electricity is conducted by different substances. Charged particles in matter. For understanding the nature of the charged particles in matter, let us carry out the following activities. Comb hair, dry hair. Does the comb then attract small pieces of paper? Wrap a glass rod with a silk cloth and bring the rod near the inflated balloon. Observe what happens. From these activities, can we conclude that on rubbing two objects together, they become electrically charged? Where does this charge come from? The question can be answered by knowing that an atom is divisible and consists of charged particles. Many scientists contributed in revealing the presence of charged particles in an atom. It was known by 19 that the atom was an indivisible particle but contained at least one subatomic particle, electron, identified by J. Thomson. Even before the electron was identified, E. Goldstein in 1886 discovered the presence of new radiations in a gas discharge and called them canal rays. These rays were positively charged radiations, which ultimately lead to the discovery of another subatomic particle. The subatomic particle had a charge equal in magnitude but opposite in sign to that of the electron. Its mass was approximately 2000 times as that of the electron. It was given the name of the proton. In general, an electron is represented as E and the proton as P. Mass of an proton is taken as 1 unit and a charge is +1. Mass of an electron is considered to be negligible and its charge is -1. It seemed that an atom was composed of protons and electrons, mutually balancing their charges. It also appeared that the protons were in the interior of an atom, for whereas electrons could easily be removed off but not protons. Now the big question was, what sort of structure did the particles of the atom form? We'll find the answer to the question below. Structure of an atom. We had learned Dalton's atomic theory in chapter 3, suggested that atom was indivisible and indestructible. But the discovery of two fundamental particles inside the atom led to the failure of this aspect of Dalton's atomic theory. It was then considered necessary to know how electrons and protons are arranged within an atom. For explaining this, many scientists proposed various atomic models. J. Thomson was the first one to propose a model for the structure of an atom. Thomson's model of an atom. Thomson proposed the model of an atom to be similar to that of Christmas pudding. Electrons in a sphere of positive charge were like currants, dry fruits in a spherical Christmas pudding. We can also think of a watermelon. The positive charge in the atom is spread all over like the red edible part of the watermelon, while the electrons are studded in the positively charged sphere like the seeds in the watermelon. Positive sphere electron. J. Thomson, a British physicist, was born in Cheetham Hill, a suburb of Manchester, on 18th December 1856. He was awarded the Nobel Prize in Physics in 1906 for his work on the discovery of electrons. He directed the Cavendish Laboratory at Cambridge for 35 years, and 7 of his research assistants subsequently won Nobel Prizes. Thomson proposed that an atom consists of positively charged sphere, the electrons are embedded in it. Negative and positive charge are equal in magnitude, so the atom as a whole is electrically neutral. Although Thomson's model explained the electrons are electrically neutral, the results of the experiments carried out by other scientists could not be explained by this model, as we see below. Rutherford's model of an atom. Ernest Rutherford was interested in knowing how the electrons are arranged within an atom. Rutherford designed and experimented for this. In this experiment, fast-moving alpha particles were made to fall on a thin gold foil. He selected a gold foil because he wanted a thin layer as possible. This gold foil was about 1000 atom thick. Alpha particles are doubly charged helium ions. Since they have a mass of 4 units, the fast-moving alpha particles have a considerable amount of energy. It was expected that alpha particles would be deflected by the subatomic particles in the gold atoms. Since the alpha particles were much heavier than the protons, it did not expect to see large deflections. But the alpha scattering experiment gave totally unexpected results. The following observations were made. Most of the fast-moving alpha particles passed straight through the gold foil. Some of the alpha particles were deflected by the foil by small angles. Surprisingly, 1 out of every 12,000 particles appeared to be rebound. In the words of Rutherford, this result was almost as incredible as if a fire and 15-inch shell of a piece of tissue paper and comes back and hits you. E. Rutherford was born at Spring Grove on 30th August 1871. He was known as the father of nuclear physics. He is famous for his work on radioactivity and the discovery of the nucleus of an atom with the gold foil experiment. He got the Nobel Prize in Chemistry in 1908. Let us think of an activity in an open field to understand the implications of this experiment. Let a child stand in front of a wall with the eyes closed. Let him throw stones at the wall from a distance. He will hear a sound when each stone strikes the wall. If you repeat this 10 times, you will hear the sound 10 times. But if a blindfolded child were to throw 2 stones at a barbed wire fence, most of the stones would not hit the fencing and no sound would be heard. This is because there are a lot of gaps in the fence which allow the stone to pass through them. Following a similar reasoning, Rutherford concluded the alpha particle scattering experiment that most of the space inside the atom is empty because most of the alpha particles pass through the gold foil without getting deflected. Very few particles were deflected from their path, indicating that the positive charge of an atom occupies very small space. A very small fraction of alpha particles were deflected by 180 degrees, indicating that all the positive charge and mass of the gold atom were concentrated in a very small volume within the atom. From the data, he also calculated that the radius of the nucleus is about 10 to 5 times less than that of the radius of an atom. On the basis of the experiment, Rutherford put forward the nuclear model of an atom, which had the following features. There is a positively charged center in the atom called the nucleus. Nearly all the mass of an atom resides in the nucleus. The electrons revolve around the nucleus in circular path. Size of the nucleus is very small as compared to the size of an atom. Drawback of Rutherford model of an atom. Revolution of an atom in a circular orbit is not expected to be stable. Any particle in a circular orbit would undergo acceleration. During acceleration, charged particle would radiate energy. Thus, the revolving electron would lose energy and finally fall into nucleus. If this were so, the atom should be highly unstable and hence matter would not exist in the form that we know. We know that atoms are quite stable. Bohr model of atom. In order to overcome the objections raised against Rutherford's model of atom, Niels Bohr put forward the following postulates about the model of an atom. Only certain special orbits are known as discrete orbits of electrons are allowed inside the atom. While revolving in discrete orbits, electrons do not radiate energy. Niels Bohr was born in Copenhagen on 7th October 1885. He was appointed professor of physics at Copenhagen University in 1960. He got the Nobel Prize for his work on the structure of atom in 1922. Among Professor Bohr's numerous writings, 3 appearing as books are The Theory of Spectra and Atomic Constitution, The Atomic Theory and the Description of Nature. These orbits or shells are called energy levels. Energy levels in an atom are shown in the figure. N shell, M shell, L shell, K shell and nucleus. These orbits or shells are represented by the letters K, L, M, N or the numbers N 1, 2, 3, 4. Neutrons. 1932, James Chadwick discovered another subatomic particle which had no charge and a mass nearly equal to that of proton. It was eventually named as neutron. Neutrons are present in the nucleus of all atoms except hydrogen. In general, a neutron is represented as N. Mass of an atom is therefore given by the sum of the masses of protons and neutrons that is present in the nucleus. How are electrons distributed in different orbits? Distribution of electrons into different orbits of an atom suggested by Bohr and Bury. The following rules are followed by writing the number of electrons in different energy levels or shells. Maximum number of electrons present in a shell is given by the formula 2n square, where n is the orbit number or energy level index 1, 2, 3. Hence the maximum number of electrons in different shells are as follows. First orbit of K shell, 2 into 1 square is 2. Second orbit of L shell, 2 into 2 square 8. Third orbit or M shell, 2 into 3 square 18. Fourth orbit or N shell, 2 into 4 square 32 and so on. Maximum number of electrons that can be accommodated in the outermost orbit is 8. Electrons are not accommodated in a given shell unless the inner shells are filled. That is, the shells are filled in the stepwise manner. Atomic structure of first 18 elements is shown systematically. Make a static model displaying electronic to accommodate a maximum of 8 electrons. It was observed that the atom of elements completely filled with 8 electrons in the outermost shell show little activity. In other words, their combining capacity of valency is 0. Of these inert elements, here is the table composition of atom in the first 18 elements with electron distribution in various shells. Name of element hydrogen, symbol H, atomic number 1, number of protons 1, number of neutrons no, number of electrons 1, distribution K shell 1 electrons, valency 1. Helium He, atomic number 2, number of protons 2, number of neutrons 2, number of electrons 2, distribution of electron K shell 2, valency 0. Lithium 3, Li 3, number of protons 3, number of neutrons 4, number of electrons 3, distributed in the valence shell K shell 2, L shell 1, valency 1. Beryllium Be, atomic number 4, number of protons 4, number of neutrons 5, number of electrons 4, K shell 2, L shell 2, valency 2. Boron B, atomic number 5, number of protons 5, number of neutrons 6, number of electrons 5, K shell 2, L shell 3, valency 3. Carbon C, atomic number 6, number of protons 6, number of neutrons 6, number of electrons 6, K shell 2, L shell 4, valency 4. Nitrogen, atomic number 7, number of protons 7, number of neutrons 7, number of electrons 7, K shell 2, L shell 5, valency 3. Oxygen O, atomic number 8, number of protons 8, number of neutrons 8, number of electrons 8, K shell 2, L shell 6, valency 2. Fluorine F, atomic number 9, number of protons 9, number of neutrons 10, number of electrons 9, K shell 2, L shell 7, valency 1. Neon Ne, atomic number 10, number of protons 10, number of neutrons 10, number of electrons 10, distribution K shell 2, L shell 8, valency 0. Sodium Na, atomic number 11, number of protons 11, number of neutrons 12, number of electrons 11, K shell 2, L shell 8, M shell 1, valency 1. Sodium, magnesium Mg, atomic number 12, number of protons 12, number of neutrons 12, number of electrons 12, K shell 2, L shell 8, M1, valency 1. Magnesium Mg, atomic number 12, already discussed. Then magnesium 12, protons 12, electrons 12, neutrons 12, K shell 2, L shell 8, M shell 2, valency 2. Aluminium, atomic number 13, number of protons 13, neutrons 14, electrons 13, K shell 2, L shell 8, M 3, valency 3. Silicon Si, the atomic number 14, number of protons 14, neutrons 14, electrons 14. K shell 2, L shell 8, M 4, valency 4. Phosphorus 15, atomic number 15, number of protons 15, neutrons 16, electrons 15. K shell 2, L shell 8, M 5, valency 3, 5. Sulfur S, atomic number 16, number of protons 16, neutron 16, electron 16. K2L8M 6, valency 2. Chlorine, atomic number 17, number of protons 17, neutrons 18, electrons 17. K2L8M7, valency 1. Argon, atomic number 18, number of protons 18, neutrons 22, electrons 18. K shell 2L8M 8 and valency 0. Helium atom has 2 electrons in the outermost shell and all other electrons up. Elements have atoms with 8 electrons in the outermost shell. 8 electrons in the outermost shell. The combining capacity of the atoms or elements, that is their tendency. Okay, combining elements of that is their tendency to react and form molecules with atoms of the same or different elements was thus explained as this attempt to attain a fully filled outermost shell. An outermost shell which had 8 electrons was said to possess an octet. Atoms would thus react so as to achieve an octet in the outermost shell. This was done by sharing, gaining or losing electrons. Number of electrons gained, lost or shared so as to make the octet of electrons in the outermost shell give us directly the combining capacity of the element, that is the valency discussed in the previous chapter. For example, hydrogen, lithium, sodium atom contain 1 electron each in their outermost shell. Therefore, each of them can lose 1 electron. So they are said to have valency of 1. Can you tell what is valency of magnesium and aluminium? It is 2 and 3 respectively because magnesium has 2 electrons in the outermost shell and aluminium has 3 electrons in the outermost shell. The number of electrons in the outermost shell of an atom is close to its full capacity, then valency is determined in the different way. For example, the fluorine atom has 7 electrons in the outermost shell and the valency could be 7. But it is easier for fluorine to gain 1 electron instead of losing 7 electrons. Hence, its valency is determined by subtracting 7 electrons from the octet and this gives you a valency of 1 for fluorine. Valency can be calculated in a similar way for oxygen. What is the valency of oxygen that you get from the calculation? Therefore, an atom of each element has a definite combining capacity called as its valency. Valency of the first 18 elements is given in the column. Atomic number and mass number. Atomic number. We know that protons are present in the nucleus of an atom. It is the number of protons of an atom which determines its atomic number. It is denoted by Z. All atoms of an element have the same atomic number, Z. In fact, elements are defined by the number of protons they possess. For hydrogen, Z is equal to 1 because in hydrogen atom, only 1 proton is present in the nucleus. Similarly, for carbon, Z is equal to 6. Therefore, the atomic number is defined as the total number of protons present in the nucleus of an atom. Mass number. After studying the properties of the subatomic particles of an atom, we can conclude that mass of an atom is practically due to protons and neutrons alone. These are present in the nucleus of an atom. Hence, protons and neutrons are also called nucleons. Therefore, the mass of an element resides in its nucleus. For example, mass of carbon is 12U because it has 6 protons and 6 neutrons. 6U plus 6U, that is 12U. Similarly, the mass of aluminum is 27U, 13 proton plus 14 neutrons. Mass number is defined as the sum of the total number of protons and neutrons present in the nucleus of an atom. It is denoted by A. In the notation of an atom, the atomic number, mass number and symbol of the element has to be written as mass number, symbol of element, atomic number, AZX. For example, nitrogen is written as N147. Isotopes. In nature, a number of atoms of some elements have been identified which have the same atomic number but different mass numbers. For example, take the case of hydrogen atom. It has 3 atomic species, namely protium, H11, deuterium H21 and tritium H31. Atomic number of each one is 1, but the mass number is 1, 2, 3 and respectively. Other such examples are carbon 12C6 and C146, chlorine 3517 and chlorine 3717. On the basis of the examples, isotopes are defined as atoms of the same element, having the same atomic number but different mass number. Therefore, we say that there are three isotopes of hydrogen atom, namely protium, deuterium and tritium. Many elements consist of a mixture of isotopes. Each isotope of an element is a pure substance. Chemical properties of isotopes are similar, but their physical properties are different. Chlorine occurs in nature in two isotopic forms, with masses 37U and 35U in the ratio 3:1. Obviously, the question arises, what should we take as the mass of chlorine atom? Average atomic mass of chlorine atom on the basis of above data, 35 into 75 by 100 plus 37 into 25 by 100. That's equal to 35.5 U. The mass of an atom of any natural element is taken as the average mass of all the naturally occurring atom of an element. If an element has no isotope, then the mass of an atom would be the same as the sum of protons and neutrons in it. But if an element occurs in the isotopic form, then we have to know the percentage of each isotopic form and the average mass is calculated. This does not mean that any one atom of chlorine has a fractional mass of 35.5 U. It means that you take a certain amount of chlorine. It will contain both the isotopes of chlorine and the average mass is 35.5 U. Applications. Since the chemical properties of all the isotopes of an element are the same, normally we are not concerned about taking a mixture. But some isotopes have special properties which find them useful in various fields. Some of them are: an isotope of uranium is used as a fuel in nuclear reactor. Isotope of cobalt is used as a treatment of cancer. Isotope of iodine is used in the treatment of goiter. Isobars. Let us consider two elements: calcium, atomic number 20, argon, atomic number 18. The number of protons in this atom is different, but the mass number both these elements is 40. That is, the total number of nucleons is the same in the atoms of the pairs of elements. Atoms of different elements with different atomic numbers which have the same mass number are known as isobars. Credit for the discovery of electron and proton goes to J.J. Thomson and E. Goldstein respectively. J.J. Thomson proposed that electrons are embedded in a positive sphere. Rutherford's alpha particle scattering experiment led to the discovery of the atomic nucleus. Rutherford's model of the atom proposed that a very tiny nucleus is present inside the atom. Electrons revolve around the nucleus. Stability of an atom could be explained by this model. Niels Bohr model of an atom were more successful. He proposed that electrons are distributed in different shells with discrete energy around the nucleus. The atomic shells are complete and the atom will be stable and less reactive. J. Chadwick discovered presence of neutrons in the nucleus of an atom. So the three subatomic particles of an atom are electrons, protons and neutrons. Electrons are negatively charged, protons are positively charged, neutrons have no charges. Mass of an electron is 1 by 2000 times the mass of hydrogen atom. Mass of a proton and neutron is taken as 1 unit each. Shells of an atom are designed as K, L, M and N. Valence is the combining capacity of an atom. Atomic number of an element is the same as the number of protons in the nucleus of its atom. Mass number of an atom is equal to the number of nucleons in its nucleus. Isotopes are atoms of the same element which have different mass numbers. Isobars are atoms having the same mass number but different atomic numbers. Elements are defined by the number of protons they possess. So that's all about this chapter. If you are interested, please do like, share and subscribe my channel. Okay, thank you.